presenter screen or you see the full screen?
Can see full screen.
Thank you. Okay, let's continue. So for this second section, right, we'll talk about more about apparent G, okay, and we talk about circular motion associated with gravity. Then we talk about the real and apparent weightlessness, and yeah. So this second portion, right, is following the first portion, but I'll go through it slightly faster already. Just now, right, we have discussed what is happening at the poles and what's happening at the equator. Okay, so let's look at the diagram again. So for the pole, right, both arrow, normal contact force, and mg are the same. At the equator, you must first acknowledge there's a centripetal force. Okay, how you know? Must be there one, because right, you follow the Earth, or you're on the same spot as Earth, and Earth is spinning, so you are spinning. So n must be smaller than mg. Okay. Then, right, what about the guy that's at a weird position, let's say at UK? At UK, right, where is the center of his centripetal, of his circular motion? If you can figure, can imagine, right, it is not towards the center of Earth. It is towards the center of some point that is above the center of Earth. Yeah, you can see this dotted circle. Yeah, so he's spinning in this circle. So his center is somewhere here. Therefore, right, the net force will be towards that point. Now, back to the next question. How do you draw the normal contact force and the G and the mg? Normal contact force is difficult. Mg is straightforward, like just towards the center of Earth. Normal contact force is difficult because, right, we don't know how it will be affected, right, by this need to provide for a net force. But we can reverse engineer. We know, right, that centripetal force, which is the net force, must be towards that particular direction. Yeah, the blue arrow direction. So you can reverse engineer. What must the R be such that the net force will be along that way? So you realize, right, that the R need to slant a little bit. So it's no longer normal, it's slightly slanted. Yeah. The degree of the slant is very minor. So when you go UK, right, you won't feel, right, oh, that your whole body slant half sideways, like to balance away the normal contact force. Okay, because it doesn't feel that way. It's too small an effect. Okay. Now come back to a idea, right, that we have talked about when we are talking about dynamics. Okay, which is, right, what is it that we are measuring when we are taking our weight? Okay, for most of you here, right, I believe I said this like countless times already. We are always measuring normal contact force. Yeah. Therefore, right, when you are at different point on Earth, okay, you will measure slightly different weights. And also, right, let's go through this hypothetical scenario. What if Earth spin faster? What would be the weight that you measure on the weighing machine? So currently, right, we are measuring something that is just 0.3% off from our real weight. Because from the previous example, right, in lecture 1, we see that the apparent G, right, is 9.80, close to 9.83, just a bit off. So it's 0.3% off. But, right, if you have the period of Earth's rotation, right, being much bigger, then, right, the net force required to provide for that will be much larger. Okay, so the difference, right, between N and mg will be larger. N will be smaller. The difference between these two will be larger. Mg won't change. Yeah. So in a scenario whereby you have a high period of, so a small period of rotation, right, you will have very small apparent weight. Yeah. Because a lot of your G, right, goes towards providing for centripetal force. Very little of your G is provided to cause free fall. Okay, That's another way of thinking about it. There is a G at the surface. The G has to provide for two things: allow you to go in circular motion and cause you to free fall if you are hanging in mid-air, yeah, which is the acceleration of free fall. In our current circumstances, right, the 9.83, 0.3 goes towards circular motion. Say 0.03 goes towards circular motion. 9.80 goes towards free fall. That's how they are splitting at the moment. Yeah, so the G measured will also change in this way. This is an animation. I'll skip. Oh no, I shall not skip because I think it's quite important. How can I activate it? I can't trigger the video. I'll skip. I'll send you the link. Okay. What that video, right, is trying to show or to illustrate, right, is a scenario whereby you have a cannon. Let me just describe it. You have a cannon, right, firing a cannonball. Okay. If, right, you fire a cannonball at a particular speed that's like quite normal, then we will expect, right, that the cannonball will fall towards Earth. Yeah. So normally, right, the cannonball will just fall towards Earth. If you fire it with a higher speed, okay, what will happen, right, is you'll still fall towards Earth, or like sort of a projectile motion path, but you'll still land. You go at a higher speed, right, you'll land further. Is there a speed, right, at this particular height that you're firing the cannon from, such that, right, it never get to fall, it never get to reach Earth? It's always falling, but it's not quite falling towards Earth. It's like falling into the next point on a circular path. Okay, you catch what I'm saying? It's like trying to fall, but it never get to fall, right? Such that, you see, normal case, right, when we fall, we actually get closer to the center of Earth, right? That's a normal effect of gravity. But right, if you are fired with a speed, right, that's larger and larger and larger, at some point, right, you'll get to a particular speed that it is actually impossible for you to fall towards Earth. Okay, you just cannot fall nearer towards Earth. You'll just fall, right, enough to the next point on the circular path. Also, there's a circular path there. You see, why is it that you can't fall towards Earth? Because, right, if not for gravity, right, you will have gone off tangentially. Yeah. If not for gravity, you actually will go off like this way. Let's say from this point. And because of gravity, right, you actually fall. But you fall onto the next point. So you end up here. If not for gravity, you'll follow this line off again. But because of gravity, right, you'll fall. And you'll fall onto the next point and the next point. So you keep on falling into the next point in the circular motion. Yeah. So for this part onwards, right, we'll be dealing with the math of how gravitational force provide for centripetal force and leads to circular motion. Okay, so let's just take a look at this example. We want to determine, right, the relationship between radius of the orbit and the velocity of the satellite first, then later on the period. This entire process, right, example 3, you must try it. Okay, especially I believe some people never do it before. They just watch. They say, okay, I understand already. I never do it before. Yeah, surprisingly, after 2 years. So what do you do? First step, always write this line. Don't write in exam, confirm penalize 1 mark. A-level requirement. Next, right, hence, right, write out. So what is gravitational force? Gmm over r square. What is centripetal force? Mv square over r. Okay. And what are we describing here? We are doing a F equals ma. Okay. We're doing a F equals to ma thingy for circular motion. Okay. So don't be confused. This first line, right, you cannot anyhow write for different situation. It is for things going in a circle, yeah, due to gravity. So you go on, right, expand, or you'll get a relationship like this. So you see that V is proportional to 1 over square root R. This is important. This tells you, right, as the radius decrease, V increase. So when this decrease, right, this increase. So smaller radius things, right, will have a bigger period, a bigger speed. And once again, right, take note, this kind of operation, right, the first step, the M always disappear. So nothing to do with the mass of the object. So whether the satellite big or small, how fast it goes, right, depend purely on the radius. That's all. And next, what about for the period? So you do the same thing, but this time around you write mr omega square for centripetal force. Cancel them out. So you have, right, gm over r cube. You shift the r over to the other side. So gm over r cube. Yeah. But then you have t as the denominator. So what if you make t the numerator by flipping the equation both sides? So you get something like this. Then you noted that front part are all constant term. So end up, right, you left with t squared proportional to r cube. Yeah. So this is yet another very important conclusion from this circular motion, which is the bigger the radius, the longer the period. T squared proportional to r cube. How do we know this, right? How do we verify? People actually have done it 200 years ago, okay? When the equipment technology are still quite poor, they use ingenuity, okay, to figure out ways to measure period. So they measure the period of all the planets, okay, that they can observe back then, which is like everything really. They can even see Pluto, which is quite good, okay. So they plot, right, the r cube against t square, and they saw a straight line. So this is what you do in linearization. How do you know the previous equation is correct? You plot t square against r cube. If you see a straight line, then this equation is correct, and we got a straight line. Okay. This law has a name, Kepler's third law, and there are 3 laws. You can go and figure out which are the other 2. Next part, right, is this phenomenon, right, whereby we have a satellite. We know that the period depends on the radius, right? Could we hence, right, figure out what is a radius that can give rise to a period of exactly 1 day? Okay. Why is 1 day important? Because that's the time that Earth takes to rotate 1 round. So if the satellite also takes 1 day to go 1 round, to someone on Earth, you'll see that this satellite is always up in the sky above the same spot. Okay. And at night, right, we do see that. When we see at night, right, you see some star, right, that looks like very, very bright on the sky, right? It's not a star. That thing, right, probably does not flicker. Real stars will flicker a bit. That satellite, right, won't flicker one. It's like very solid. It's just always there. So that's a satellite. And you may argue, right, and you say, hey, but that satellite, right, never move. What? So the satellite got move. What? Daytime, I don't see it. Don't be caught. Daytime, you can't see satellite. Daytime, you only see the sun. Yeah. So it only appear at night, but it's always there. Okay. So this example, right, we'll go through it to figure out the radius of the geostationary satellite. So you do the same manipulation as before. This time round, substitute in number. I just want to remind you, right, how we do this kind of calculation, right, and minimize mistake. You always, right, group the coefficient together. Here you cannot just group everything. Then you group the indices together. Then you combine them at the last step. So you take the number times number times number times number, then times the net of the power. So this will minimize mistake of this kind of terms. There's too many terms already. Yeah. But back to this. We reckon that the R, right, end up is 7 times radius of Earth. Or how you know it's 7 times? I got one, okay? Because Earth's radius is 6.4 times 10 to the power of 10 to the power of 6. Yeah. So if you times 7, right, it's 42. Or 6 times 7 is 42. So that is 7 times radius of Earth. Okay. What else I want to say? Oh yeah, what other condition, right, must geostationary satellite have, right, so that it is indeed geostationary? Because, right, to get a period of 24-hour, right, all it needs is that period that we just calculated, or around 7 times radius of Earth. But that doesn't make it geostationary yet. Geostationary means, right, standing on the same spot, you'll see at the same spot on the sky. It doesn't move on. A non-geostationary satellite, right, with 24-hour period, right, can go like this. Oh, but this is not geostationary because, right, you'll see that half the day is like in the northern hemisphere, half the day is in the southern hemisphere. Okay, so geostationary, right, got another characteristic. It must be, right, in the equatorial plane. Okay, and same direction as Earth rotation. And finally, right, no more, just 3 conditions. Okay, so when you want to describe, right, what are the conditions for geostationary satellite, all these 3 must be there. Yeah, let me ask you this question. Is this orbit possible? Anyone want to just try answer? Shout out your answer. Zhongnan?
No.
Okay. Answer is cannot. You see, if you have such an orbit, right, the centripetal acceleration needs to be towards the center of Earth, or center of its motion, which is like here. But, right, gravity is this way. That's a poor arrow. How do I undo it? I don't know how I undo this drawing, but never mind. Gravity is towards the center of Earth. So you see, these 2 arrows cannot match. So not possible. Yeah. Similarly, this one also cannot. This one also cannot. So all possible orbits, right, must have Earth's center as its center, nothing else. Okay. So that can rule out a lot of funny cases already. Okay, excessive animation. What are some of the benefits, right, or application for geostationary? Let's just go through these points. Well, it's always fixed. You don't need to go and calculate, oh, where is it? So once you know, like, oh, it's above Singapore, we have one above Singapore, one above a particular city in India, it'll always be there. Okay. And why do we use geostationary satellite? One obvious advantage, right, is because it's far enough. Okay. So if you stand from the stationary satellite point of view, right, you will see a big enough patch of Earth compared to another satellite, right, which is like near Earth's surface. You only see a small patch. But what's the downside? When you see a big patch, right, also means that if you everything the same, if whatever that you're trying to send signal with is the same, right, then for geostationary satellite, right, it's weaker. Okay. And if you're taking photo, then your resolution is also poorer. Yeah. And also, right, you can't cover polar region because, right, it's simply not possible to reach the poles. Yeah. I mean, who wants to cover polar region unless you're Russia lah? Huh? And indeed, right, Russia have their own satellite. Okay. Which is not just, it's just a weird shape. It's called ammonia orbit. Okay. It came out in one of our blog tests before. And that is to cater, right, to Russia's kind of needs. or you spend more time in the northern hemisphere than the southern hemisphere. Yep. What is this slide? I forgot what it is about already. Let's skip. Different kind of orbits, just know the names. I mean, not even necessary, but okay. You see, what we are classifying them as is by the radius, or how close is it. And yep, this is the HEO. This is, if you see the this thing, right, is like off to one side, offset to one side, right? If it's offset to the North Pole, right, you spend more time in the North Pole, like quite obvious, right? Than the South Pole. So if you are a country in the Northern Hemisphere, right, you want to use something like this. Let me skip. Okay. True weightlessness. Let's go with go into the idea of weightlessness, compare the different types. Number one, right, true weightlessness, no gravitational field. Okay, no gravitational force, full stop. How do you achieve this? Go to somewhere, no planets nearby. Yeah, that's the only way. Another scenario, right, is whereby you have two masses and only two masses. Don't complicate with more things. And let's just say, right, Earth and Moon system. Yeah, somewhere in between, right, Earth and Moon are always actually playing tug of war. If you are nearer to Earth, right, Earth will pull you stronger than Moon. Yeah, too close to Moon, Moon will pull you stronger than Earth. Somewhere in between, you'll find a balance point. They pull you with equal strength. So that's where, right, you will expect the net G to be zero. So that's another point, right, whereby you feel weightless. Okay. On the other hand, right, what is apparent weightlessness? Is simply, right, no contact force. I've explained this before, right, in past lessons, right. You see, we feel our weight not by the real effect of weight, but we feel our weights, right, due to the interaction that we have established, right, between us and our surrounding. For example, when I'm seated down, right, the contact force at my butt, okay, makes me feel heavy, because I feel, right, the pressure on the chair, I feel it at the butt. So you see, what I'm feeling, right, it's not my weight. I'm feeling, right, the normal contact force. Similarly, if I'm standing for too long, I feel that my legs feel heavy, or my toes don't feel comfortable. That's because of normal contact force. So if you were to feel weightless, right, you actually don't have to have no G. What you just need, right, is to have no normal contact force. And yep, so that is what, right, apparent weightlessness is about. So if you allow, right, the environment to accelerate at the same acceleration, right, as G, then you will have no normal contact force. Yeah, you can see the graduation in this scenario. Okay. See here. Skip. This video you can see on YouTube. You go and search, right, Veritasium Air Zero. Okay, Air Zero G. You see the background here. Watch the video. So they went onto a plane that is meant to simulate gravity. So this plane, right, will drive up to some great height. Okay, fly for a while. Everyone get ready. Then for a brief few minutes, right, this plane, right, will switch off the engine. Okay, orientate the actually I have the diagram. I forgot about it. Yeah, will orientate the plane, right, at the correct angle, right, and then switch off the engine. And then for a brief period, there will be no G. Yeah. So you see, it's the blue color zone. The plane is like pointing up, right? It's like throwing a paper plane, right, into the air. So this paper plane, right, just go through a projectile motion. But what will people inside the plane feel? Because, right, the plane, right, is simply free falling as part of a projectile motion. So people inside, right, will feel the same will have the same acceleration as a plane. So there will be no normal contact force. So apparent weightlessness. Yeah, people actually pay tens of thousands of dollars, right, to take this plane. And there's one pop star, I don't know who, I forgot already. They film an MTV on this plane, yeah, whereby everything is like all over the place, yeah, quite cool. I'll skip, I mentioned this already. Same for the International Space Station, okay? So when you are in outer space, right, you are going in the same circular motion as the space station, okay? Thus, right, the person inside, right, will have no normal contact force from the surrounding, yeah, because both you and surrounding accelerating at the same g, yeah. Okay, here, right, is yet another effect, which is, right, artificial g. This is not in syllabus. Actually, no. This sometimes is in syllabus. You see, if, right, the absence of weight, right, that you feel is due to the absence of contact force. Could you, right, go the reverse direction and say, right, what if, right, I create the presence of contact force to mimic the presence of gravity? Yeah, I say again, you see, the absence of contact force, right, makes you feel weightless. Similarly, right, you can go the reverse direction, which is, right, the presence, you create contact force in such a way, right, or in an environment that actually have zero g, you create contact force to make you feel that there is g, because, right, you feel contact with your surrounding. And we actually do that, right, in in science fiction. You know the movie, right, called The Space Odyssey, or in fact, right, most space movies, you always see, right, the spacemen, the astronauts, right, inside the spacecraft, right, there's a part whereby they are living quarters, whereby, right, they can jog on the treadmill, walk around, do things just like normal. And, right, when the angle, camera angle, right, zoom out, you'll see that that portion, right, is always on this spinning centrifuge. The thing is, right, spinning, right, to cause the surrounding, right, to exert a normal contact force on you, so that you feel that there is a contact. Okay, so that is artificial g. Diagram will look like this. Okay, so you have a centrifuge, right, that's always spinning quite fast, in fact. So to provide for the centripetal force, normal contact force needs to be there. Yeah. So you work out. Let's say, right, I want to create a g that's close to 9.81. Okay. And, right, my radius of this centrifuge thing is, let's say, 100 meters. Pretty large already. 100 meters is like 2 football field long. Yeah, the radius is 100 meters. The entire centrifuge is 2 football field long. So how fast does this thing spin? You can work out. One period is less than 1 second. Okay, so this thing had to spin really, really fast. This is what I meant. Look at space movie, right? This is another picture. Yeah. This is what they call the space colony. Yeah. Because before you go to the actual place, right, you need to spend quite a bit of time in space. If you are moving a lot of people there, right, you want living conditions which are normal to them. Also create something that's really huge and spin this whole thing. You will see this inside Interstellar also. Okay, and that's the end. Whoa.